Okay, like I mentioned before, this is the start of our data analysis section. Today we're going to go through signal processing, discuss what signals are, and so forth, how they're captured, types of operations you can do of them, and we're heading towards looking at Fourier transforms in the next lecture, and wavelet transforms, and so on as well. Okay, so a signal is just simply a measurement of the flow of information over time, position, or some other known independent variable. For example, for position, we can consider the temperature of the ocean with respect to depth. So you can consider a single location in the ocean and then consider how that temperature changes as you go down in depth. An example for time, we can consider the acceleration of the tip of a wing, of an aircraft wing. So of course, both of these, temperature and acceleration, can be both spatially varying measurements as well as temporally varying measurements. But generally, we're going to deal with signals that depend on time in this class. So, like I said, we're going to really focus on time dependence. Generally, that's just what you're studying when you're considering vibrations or motion. And I'll also say that a lot of the methods we will study throughout here can be applied to other types of signals, though we're primarily going to focus just on time domain. All right, so there are two types of signals. The first are those that are continuous time, also known as analog. Continuous time signals, things like voltage, strain, accelerations, temperature, and so on. So these are types of signals that are continuous in time, meaning you can, assuming that time can be infinitely divided, you'll always find some type of signal at that time. The second type are discrete time signals. These are things like the daily min or maximum temperatures, things like yearly populations, lap intervals in races, and then other types of discrete dynamical systems. Etc. And most importantly, sampled analog signals. So when we do a measurement, we sample typically an analog signal, and as a result, produce a discrete time signal. We do other things when we do measurements as well, which we'll get to, but one of the things we do is sample it, which converts that analog signal into a discrete signal. We're now going to talk about both what sampling is and what quantization is as well. And this is important because it lays the foundation for understanding measurements and then understanding what we can do with those measurements. So sampling is simply a discretization in time. So in that case, we go from some continuous time t to a collection or a vector of time steps, 0, delta t, 2 delta t, all the way up to usually some finite time big T. Although in general, a discrete time signal can go to infinity. It doesn't have to be a finite collection of points. Quantization then is discretization in terms of amplitude. Okay, and we'll discuss what each of these looks like using this example S of t. So we can consider some analog signal S of t shown here, and we're going to sample it at the intervals delta t, 2 delta t, and so on. So at each of these points, we will sample our signal and we will simply get, we'll lose all of the information between our sampling intervals, and we'll only get these red points in our vector representing this signal. So here, we will write the discrete signal S with square brackets and n representing the discretized points. So here, sampling this analog signal S of t results in a discrete time signal, which we'll write as S of n using square brackets, and this occurs at times n delta t for n equal to 0, 1, 2, and so on, all the way up to, if it's a finite sampling, all the way up to big N. It does not have to be finite, though if we're thinking about a measurement, those are normally usually finite duration. But in general, these don't have to be finite. When we talked about maps last week, those are dynamical systems that could be constructed from analog signals that could then be studied for infinite time, infinite discrete time. When it comes to doing measurements, we obviously will have to truncate and stop a measurement at some point. Though you could have continuously going measurements, which although still will have finite duration, don't necessarily have finite duration as of right now. Okay, let us move on and take a look at what quantization looks like. So when we quantize a signal, we are discretizing the amplitude, and this usually has to do with limitations of measurement equipment, particularly in terms of like a voltage range. And based on that voltage range in that measurement equipment, you will have what is a minimum possible amplitude you can measure and a minimum possible difference between amplitudes. So there's a minimum interval. And as a result of that, we're just going to exaggerate it in this plot. What you end up with is stepping. Oops. Something like that. And at least in my lab with the equipment we have, this quantization is usually below the noise floor, but there are cases where you can observe this behavior as well. All right, so what we really want to talk about are what are known as digital signals. And these are signals that we'll be working with in this class, and they're both sampled and quantized. So in this case, let me draw some dashed lines here. We're not only going to have this quantization effect, but we're also going to have the sampling effect, where we'll be losing information through both sampling and also through the quantization. I'm just going to zoom in here. So what can happen is that the real value might not actually align with the point that we're sampling. So the real value might be, in this case, might be a little bit, lower than what our system is capable of measuring. And then this goes into the error that we accumulate from that measurement. All right, so before we said S with the square brackets of N. That was our sampled signal. The quantized signal, we will just add a Q subscript to the S there. When you quantize it, it is still a continuous time signal. It just has a discrete amplitude values, meaning that it has a finite resolution in terms of amplitudes. A digital signal, which is what we're going to be dealing with, is both sampled and quantized, and by doing that, we end up with the signal, which we can say, actually up here, let's just add, in the green line, we had our SQ of T, still continuous. Here we're going to have, again, these are not just the dots, this will be SQ of N with square brackets, and SQ of N, the square brackets. And we use the square brackets to indicate that it's discrete time. And then this is available at times n delta t for n equal to 0, 1, 2, so on. So why should we care about digital signals?
There's no saving information.
What do you mean by saving the information?
Collecting the data, we need digital ones. No,
Why do we need digital ones? Why couldn't we use analog?
we can process it with the computer.
You're like 75% there, but it's simpler.
Simply.
Yeah.
The interval that we measure the data, those delta t, the spaces.
Is that why we care about digital signals? Because of the interval?
It's important how we fast or slow we measure the continuous time.
It's true, but not an answer to the question posed. All right, so Mohammed had a key word in his answer. That key word was computer.
Equipments, limited resources.
Like a 1, 0.
Computers are only digital. They don't work in analog signals. They only work in digital. So even when you're dealing with, a continuous time simulation through ODE45, it's still a digital signal that it's producing. It might be a continuous time signal that you're simulating, but the information itself is still digital. So the answer is that computers only work in digital signals. And before computers, and maybe after computers, this was way before my time, they used to record these analog signals on like pieces of paper. And they'd have like a seismograph or something, and then it would feed out this graph. That was before my time. So I don't have any information other than to say those things existed. And so if it was before my time, it was before your time as well. So luckily, we don't have to deal with that kind of stuff. All right. So both sampling and quantization lead to potential loss of information, like I mentioned. With sampling, we're just throwing out whatever in between the points that we sample at. With quantization, we are just, the measurement that we can get is at the minimum, difference in amplitude, or the minimum amplitude resolution that the equipment or the system we use has. Okay, so the good news is that if all of the information in a signal occurs below some frequency FB, then it can be sampled at a rate of Fs greater than 2 times FB, or for some delta T less than over 2 FB. Without any lost information, and this is known as the Nyquist-Shannon sampling theorem. Has everyone here heard of the Nyquist theorem before? Has anyone not heard of it before? It comes, in control theory, but it really comes down to signal processing is where it rose. So that's the good news, is that we have the Nyquist-Shannon sampling theorem. The bad news is that very few signals are limited to some discrete frequency band. Most signals are broadband, and even with very high sampling frequencies, you can get a lot of errors through both noise and through aliasing. And in fact, any vibrating structure is automatically not going to satisfy Nyquist-Shannon sampling theorem, because every vibrating structure will have an infinite number of modes, whether or not we're thinking linear or normal or nonlinear normal modes. In both contexts, they have an infinite number, and therefore they have an infinite number of frequencies where it's oscillating at, so you cannot define an FB that captures all of the modes, because FB would need to be infinite. And you will never have infinite bandwidth in terms of what you can measure in a system. All right, so has everyone heard of aliasing before? All right, Sam is shaking his head no. I'll try to get you some resources on it, but the key thing is that aliasing is just a phenomenon where high frequency components will appear at lower frequencies in the sampled signal. So you sample at some frequency, let's say you're sampling at Fs, and in the case of a vibrating structure, the structure is, let's say, just oscillating at some frequency above Fs. That component or mode will then appear at a lower frequency in your data, and the bad news is that you'll have no idea whether it's a real mode or if it's been aliased if you haven't dealt with this before sampling. So the key thing I want to get across here is that aliasing must be addressed before digitization. Digitization is this process of converting from an analog to a digital signal involving both sampling and quantization. And there's a little bit more to it than just that, but we're not gonna go into that because this is not a class about electronics. So the key thing is that if you do not address aliasing and you're not, very lucky with your frequency content, exceedingly lucky, I would say, If it's not addressed before you do the digitization, before you do your sampling and quantization, then the resulting data is typically useless. Meaning that it's not physically representative of the real structure. Okay, so the majority of measurement systems, and certainly any, modern vibration measurement equipment, will deal with aliasing before the digitization. They will usually come equipped with electronic filters built into the DAC, the data acquisition system, that will filter the analog signal and remove all of these components above your sampling frequency, above 1/2 of the sampling frequency. In fact, they end up removing a little bit more than that. As a result, you will not have any effects of aliasing in the measurements that you take. There are some cases where aliasing is useful, and one example is the Navy was trying to measure an extremely high frequency acoustic response. And in that case, they didn't have the equipment that could measure that, and they used aliasing as a way to measure that phenomena without that being a problem. In their case, they didn't have any frequency below the Nyquist sampling content frequency that they were interested in capturing, so it didn't affect anything there. But that was like the only case I could find online in a short search. So very rare and not in the scope of this course. Okay, so the good news for you guys is that every signal that you get from me will have already been dealt with in terms of aliasing. You'll never have to deal with aliasing. The measurements that we do in my lab and in most majority of laboratories are equipped, most measurement equipment is now equipped with anti-aliasing filters, though that's something you should check when you're ordering equipment to make sure. All right, so quantization will lead to irreversible losses of information. The effects are nonlinear and can only be described in statistical means, and not in the context or scope of this course either. Just know that due to quantization, we are irreversibly losing information that cannot be recovered, and you cannot predict what you've lost. You cannot really estimate that, except for in terms of statistics. Okay.
Because say you quantize it with the 8-bit or 32-byte bits, and it doesn't know anything about it, right? About the analog signal. It just, it captured those points, right?
Yep. It usually has a lot of times. Well, you can calculate this, the bandwidth of the amplitude that's allowable. Not relevant to what we'll do, but I mean you're right. For cases like, let me put the laser like right here. The point is here, but the system is going to report a value here, and the measurement system or however you're quantizing this has no idea what this value is. And so again, this is why it's irreversible, because you have no idea what it is. The computer has no idea what it is. Nothing that we've recorded has any clue what that value is. And it doesn't even know that it's changing, that the difference here is changing. It's totally, irreversible, completely we really can only study it in terms of statistics, and it's nonlinear as well. The good news is that, at least in my work, this is not a problem, because we study large displacement oscillations on the order of usually centimeters, millimeters to centimeters, and the quantization error is on the order of like maybe tens of micrometers. Is usually below our noise floor, so it's normally not a problem for the kinds of things we study. But that doesn't mean that it can't be a problem for other kinds of measurements. It's just something you should be aware of. And certainly this stuff used to be a problem like, I don't know, 30 years ago or something. You know, and if you're trying to push the boundaries of what can be measured, that's where these things will probably be a problem. And the stuff that we study won't really be an issue. But it is there and you should be aware of it. And then also things like the Heisenberg uncertainty principle pop up as well that can be studied and need to be taken into account. For what we are going to study, that won't really be a problem for us, fortunately. All right, any other questions? All right, in this case, we're going to talk about signal processing. And there are 3 types. First is just analog signal processing. And these are 3 general types. You can have more complicated combinations of these or subcategories and so forth. We're just going over an overview. So first is analog signal processing. The second is then signal processing of digital signals. And then third, digital signal processing of analog signals. And like I said, these are like the 3 basic categories, and you can combine them to make more complicated flows. Like you could process an analog signal and then convert it to a digital signal, process that digitally, and then convert it back into an analog signal. You can do all kinds of things, whatever you want. Though, of course, at each process of conversion, you are going to lose some information. Okay, in terms of analog signal processing, we're typically taking an analog signal in, and then doing some analog signal processing to it. So in this case, analog signal processing is actually something physical. It is like an acoustic filter or a circuit that you've designed, or if we want to go there, we could think of metamaterials that are designed to filter out some type of elastic wave. Or you could even think of like a flow straightener used in like diesel engines to straighten flows. So in this case, we're thinking some type of physical component something like an acoustic filter or some type of circuit, so on. So in vibration measurement equipment, I mentioned they do all the anti-aliasing. They deal with aliasing before they do the digitization. They have anti-aliasing filters that act as analog signal processors that filter out the high frequency content before the digitization occurs. And then the output of this analog signal processing unit, or whatever it is still going to be an analog signal. Okay, in the case of digital signal processing of some digital signal, it's going to be exactly the same as above, just with digital signals. So we have some digital signal. It's going to go into our digital signal processor. And then we're going to get back out of that a digital signal. And in this case, the DSP is going to be some type of computer. Or a very special piece of equipment that has been designed specifically to do this. Those do exist, but generally it's going to be a computer or a computer-based. Yeah, and so like I said, digital signal processing is performed using a computer or a DSP, a specialized microchip or specialized component specifically designed to deal with digital signals. But mostly you're just going to deal with this stuff on a computer. You can also do digital signal processing of analog signals. And in this case, we're going to start off with an analog signal. That's going to go into an analog to digital converter. Also known as an ADC. That becomes a digital signal. This is the case where we have a measurement done. The digital signal out of that ADC represents the measurement we've taken. You'll then do some type of digital signal processing. And out of that we'll get again a digital signal. That then goes into a digital to analog converter or a DAC. And out of that we'll get an analog signal. Okay, so pretty much everything we are going to study is going to be a digital signal processing or part of digital signal processing. And we are certainly going to implement it using computers. So digitally, some of the things we do, it may be possible to produce analog versions. I'm not 100% certain that's feasible. It's possible. We, however, will not be dealing with anything like that. Trying to study analog versions of a digital signal processor. Okay, the last thing I wanted to outline here is just what like a typical vibration measurement would look like, just given the context of the class. So we're going to start off with some physical response. Like an acceleration, velocity, something like that. We're going to get back out of that an analog signal. The response is an analog signal. We have some type of sensor. The sensor converts that response into voltage, which is still an analog signal. So we get back out here a voltage, still an analog signal. This then passes into anti-aliasing filters. And it could go through things like amplifiers and other things as well. We're just giving a general overview here of what happens. And then after that, we still have this analog signal, and then it passes into an analog to digital converter. And the ADC is what does the sampling and the quantization as well. And afterwards, we get a digital signal out of that, and then this goes into a computer somewhere. And you know, each little block here is more complicated than shown here. You know, the physical response could be exceedingly complicated. Sensors, there's many different types of sensors you can study, even many different types of accelerometers that people use. Anti-aliasing filters are some type of circuits, and they're all adjustable now depending on what you want to sample in your bandwidth. The analog to digital converter has at least 3 different components that you can consider, like a zero-order hold, and so on. We'll skip the details. And then we deal with computers all the time, but they're still complicated as well. It's not an electrical engineering class, so we're not going to go through any of that stuff. In fact, we won't really do anything with this. I just wanted you to be aware of how this stuff works. Okay, we're going to now talk about discrete signals, because that's what we're dealing with, and the types of processing you can do. And a digital signal is a type of discrete signal, so it falls underneath this as well. All right, so let's consider the discrete signal x of n, and we can say that this signal, for example, is equal to x of n is equal to the sequence 1, 2, 4, 8, so on. And here it can extend to infinity. So, I mean, obviously a real measurement on a real computer is going to be a finite list of numbers, but in general, these discrete signals just can go on forever, like we saw for maps. And in fact, they can extend in either direction. So we could have x of n, whoops, we want a square bracket there. X of n is equal to curly brace of dot, 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 minus 8, minus 4, minus 2, 1, 2, 4, 8, dot, dot, dot. So they can extend infinitely in both directions. Kind of like how we talked about maps that were diffeomorphisms, how you can go backwards in time or you can go forwards in time. Same thing here, discrete signals can extend in either direction. Like I said, we're going to typically deal with finite signals because we have finite resources, meaning our computers cannot store infinite numbers, infinite lists of numbers. They might be able to store very, very long lists, extremely long lists that seem, super long to us, but they're not infinite, and they'll never be infinite. So we're always going to typically we're going to deal with finite signals. When we're dealing with maps, those are signals that would extend to infinity. Okay, so let's talk about some signal measures. There are first 3 types of sums that you can define for discrete signals. The first we're going to call the discrete sum, and we'll write this as big S sub d is equal to the sum from lower n equals minus infinity to infinity of xn. And so here we're just simply summing up all of the values. Or if it's a finite signal, we can say that SD is equal to the sum from n equals minus m to big N of x of n. So here we're just simply summing up the components. The second kind is the absolute sum. We will say SA is equal to the infinite sum from n equals minus infinity to infinity of the absolute value of x of n. Or in terms of a finite signal, we'll say SA is equal to the sum from n equals minus m to big N of the absolute value of x of n. And then lastly, we have what's known as the cumulative sum, which we'll call S sub c, and this is now a function of n, and it's equal to the sum from lowercase k equals minus infinity to n of x k. So in this case, we're summing all of the components up to the time n. Or in terms of a finite signal, it will be SC still of n is equal to the sum from k equals minus m up to n of x k. Okay, so the signal energy is going to be defined as, we'll use E is equal to the infinite sum from n equals minus infinity to infinity of the absolute value of xn squared. Or for finite signal, E is equal to the sum from n equals minus m to big N of the absolute value of n squared. So the signal energy is useful for aperiodic signals, but not useful for periodic signals because it ends up being infinite as a result of that periodicity. So if you were dealing with a periodic signal, we're instead going to look at the average power, or look at we're either going to look at the average value of the signal, or we're going to look at the signal power. And so the average value, we can say x av will be equal to 1 over n times the summation from n equals 0 to big N minus 1 of x of n, where n inside 0 to n minus 1, where this represents a single cycle. So if you have like a purely sinusoidal response with only one frequency, let's say, the average value is not going to be very useful because you're just going to get back 0. And that's where you'd want to look at the signal power instead. But for just a general periodic response, which doesn't have to be sinusoidal, the average value can be useful. All right, so then the signal power P, this is equal to 1 over n, 1 over big N times the sum from n equals 0 to n minus 1, big N minus 1 of x of little n, where again here, wait on. Should be the absolute value of x squared. Where again, this interval represents one cycle. Okay, we're going to go through some operations on discrete signals, and then we have one example which I will do part of, and then you will do the rest of it. And then we'll have a few more things to say, and then we'll be done. All right, so considering operation on discrete signals, the first thing we can do is to introduce a time shift. And this is where we're going to describe or define a delayed version of our signal x. And in this case, you could say something like y of n is equal to x of n minus a, where we're simply shifting it in time, delaying it by the value a. And both n and a are integers in this response. It doesn't make any sense for a or n to not be integers for this type of signal. Okay, you can also do a folding operation. This is equivalent to mirroring about n equals 0. And if we fold that signal x of n, we will get that y of n is equal to x of minus n. The next thing is decimating, which is just a simple reduction in the sampling rate to compress that signal. And so you could say that y of n is equal to x evaluated at 2n, where y of n is now the signal that results from decimating x of n by 2. So this is equivalent to decreasing the sampling rate by a factor of 2. And like I said, decimation removes samples. You can also do an interpolation, which is an increase in sampling rate that expands the signal. And in this case, we can say that y of n is equal to x of n divided by 2. And then y of n results from interpolating x by a factor of 2. And so interpolation will add samples, and it can be done using many different approaches, such as a linear step, spline interpolation, and many, many others as well. And we're going to take a look at an example of how decimation and interpolation act on a particular signal. All right, so we're going to consider the following signal, which is x of n is equal to the curly brace of 1, 2, 6, comma 4, 8. And what we're going to do is in step A, or part A, we're going to do a step interpolation, and then we're going to by 2, and then we're going to do a decimation by 2. In part B, we're going to decimate by 2 and then do a step interpolation by 2. And then in C, we're just going to make a comparison of these two results. So I'm going to do part A, and then you guys will all do part B. And then we can compare them as well. Okay, so for A, we want to do a step interpolation by 2, and then we're going to decimate by 2. So we start off with our signal x, and is equal to 1, 2, 6, 4, 8. From here, we're going to step interpolate by 2. Which is going to result in xn is equal to, in the step interpolation, we're just taking the previous value. So we'll have 1, then 2, 2, 6, 6, 4, 4, and 8, 8. From here, we're going to decimate by 2. In this case, we're going to take just only the odd values, do just decimating by 2, and then xn is going to be equal to 1, we'll skip the next one, 2, skip the second 2, 6, skip the second 6, 4, skip the second 4, and then 8, and then we again skip the second 8, and we end up back where we started. So from this, we can at least see that the decimation is the inverse of interpolation. Okay, with that, you guys are now going to work on part B.
Can you explain how to get the interpolation by 2?
Sure, so this is using what's known as a step interpolation, or just taking a previous value interpolation. And so if you were to plot this, you would just see steps.
Oh, okay.
Yeah, this is a simple example to illustrate a point. But that doesn't mean that you have to use step interpolation, and generally you would not, because it's not very accurate. You would generally use something like a cubic spline, or some type of Hermite interpolating polynomial. It depends on what your application. There's many different types of Kima splines, a whole bunch of different things you can use.
And how does the factor 2 play here?
How does it affect what?
The factor 2 play here.
Sure. So when we say in step interpolate by 2, what we're saying is we're increasing the number of samples by 2 in this case, and the step interpolate is the method by which we're doing that. So we wanted to step interpolate by 3, we would increase the number of samples by 3, and then we would keep the ones. We would have 3 1s, 3 2s, so on. The number has to do with the increasing the number of sampling points. And then decimating is reducing the number by 2. And in this case, we're taking each of the every odd one. Though you could specify that you want to take the even ones. Although in this case, those even ones would have been generated by the interpolation. And in this case, you get the same answer. Okay. Okay, so let me put that back up there. So one thing is that n starts at 0 in this example. Though you could choose to decimate and keep only so when you decimate here, because n starting at 0, we're keeping the 1, 6, and 8. If you so wanted to, you could decide to keep the 2 and 4 instead. This is something, when it comes to doing this in like MATLAB, you get to decide that in general. Unless if you're doing this manually by just sampling endpoints in the vector itself. If you're using the decimate function, that function will not only reduce the sampling rate, it will also filter things as well. So you don't get to control that. All right, so but for this simple signal, if we start by decimating by 2, keeping the first entry, we'll end up with 1, 6, and 8. We can then step interpolate by 2, and we get back 1, 1, 6, 6, 8, 8. And then part C, the answer is that the resulting signals are just simply not the same. And the reason is that the decimate is the inverse of the interpolation, but not necessarily the other way around. Interpolation is not necessarily the inverse of decimation. Not to say that you can't find a case where it is the inverse, but certainly not always. Okay, so that means that if you must decimate and interpolate, then it's better to interpolate first and then decimate your signal. In my opinion, it is just better to avoid interpolation to begin with, and you do that by sampling at a high enough rate to capture everything that you want. And you can always decimate a signal, but you can't always interpolate a signal. And this is why I think it's just better to sample high, because you lose nothing and you can decimate and remove stuff without any loss of information. When you interpolate, you introduce error into your signal. So other operations include things like filtering, which we've mentioned but haven't discussed. We'll go through filtering at some point. Transformations, Fourier transforms, Weyl transforms, etc. That's where we're going next. And then things like signal decomposition, which is where we're going to go after we do transforms. And then there are many, many other operations you can do. A lot of what we'll discuss will come down to stuff like this. Okay.